So good morning, everyone, again. Uh, I'm going to introduce myself again uh, in case anyone happened to arrive in the meantime. My name is Antoine Soloy. I'm a postdoctoral researcher at JPL. I'm working essentially on coastal dynamics through remote sensing and numerical modeling. Today, I'm going to present you an introduction to numerical modeling of coastal hydrodynamics, and we're going to basically learn the basics of how to create a simulation of water flow from scratch. We're going to use for that the model called ANUGA, which is a Python module that should be able to work on any computer that's able to run Python. So first, why do we need to model hydrodynamics? Well, everyone here should have their own reason since you're here to learn this. But you know that the coastline is a complex environment, especially in Louisiana, and it imposes some issues that we want to be able to either predict or to be able to simulate in case we don't have observations there. That could be for different reasons, for environmental management, flood risk mitigation, and other types of projects. So there are many tools that exist to do this. Here you have a non-exhaustive list of those. In our case, we're going to be using something called ANUGA. As I was saying, it's a Python package, and it only resolves the flow of water. So it's not able to predict sediment transport nor morphodynamics. It's purely hydrodynamics. It's actually both a strength as well as a limitation because it's very flexible. It can be run on any distribution. Since it's in Python, it's lightweight. It's also parallelizable, and it works on an unstructured mesh, which can be refined locally, which makes it very handy. One other thing is that it's supported natively by QGIS. So any output of ANUGA, you can basically slide and drop in QGIS, and QGIS will open it. Through the deltaic mission, we've created a number of such models for the Louisiana, for the Mississippi Delta region, some of which are focused essentially on the Wax Lake Delta and Atchafalaya. And for those were essentially made by the University of Austin. And JPL also made a larger domain, including both this Atchafalaya Wax Lake Delta region and the Terrebonne Basin. So we have 3 periods of time that are covered: spring 2016, spring 2021, and fall 2021, which correspond to the periods that we have in situ and remote sensing measurements. You are already able to download the spring 2021 model for this, and it works the same as the DEM that you just downloaded. So there is a link to the page here. You can just download the results day by day. And so this is what it looks like. You have here on the right this one of those models. That's a prediction basically of the water surface elevation in this huge area. You see that it's close to 1 to 200 kilometers in width. And so, yeah, what we're going to do in this next 15 minutes is explain how this was created. And the rest of the workshop on this topic will be basically to teach you how to make this yourself. So we're going to take a small sample of this part. You will be able to choose the region that you want to focus on and to basically create the same simulation. So the first thing that you want to do when you create a model, and what we did here, is defining where your domain is gonna be limited. So the domain boundary. For this, 3 or 4 important parameters are: first, you want it to be as isolated as possible. You want to be able to basically isolate your basin. So you want to put your boundaries over natural levees or mountain ridges if you're in a more mountainous region, so that there is no exchange between inside and outside your domain, or at least as possible. It's not always possible to do it. There will be some compromises to do. For instance, here we have the intercoastal waterway that crosses the model. And so if you don't have data about how much water is flowing in this channel, well, it's going to be one of the limitations of your model. Another thing to consider is the data availability. You want to make sure that just like the intercoastal waterway, you do have data or not. You want to be aware of it, and you want to know where this data is coming from. For instance, in this model, we have 2 discharge inputs, which are Calumet and Morgan City, and that's why the model is stopped at the border. The limit of the domain is located at these locations. We also are using tides here at Eugene Island, which are imposed all over the southern boundary here. You will notice that this boundary is not fully straight. It doesn't have to be, but it's another compromise that needed to be made here, because the DEM that you downloaded doesn't go as south as we would like. We want to be sure that the tide remains consistent all over the coast. And if you have variations in depth, it might be a problem for the tide to propagate correctly. So here we needed to expand a little bit the DEM south. So this DEM was combined with another DEM provided by NOAA that was going a little bit more south, but it was not going more to the west. So there was a trade-off here, which explains the squiggly shape of the southern boundary. Another DEM adjustment that was made here is that all the channels in the wetlands are not perfectly rendered in the DEM that you downloaded, which means that if there is a channel there in reality and it's not in the DEM, it might not let the water flow correctly. So what we did, and what you're going to do also in the hands-on exercises, is that we used the center lines that we've downloaded and carved manually or some channels to ensure hydrologic conductivity, connectivity. Sorry. And if I was to zoom in here, I don't know if I can do that. Oh, yes. You could see that, for instance, the parts that are just east of the river here are, let's let's say, not as blue on the left panel than on the right panel. Some extra channels have been carved in this part. So that's in order to let the water flow. In case you want to do it at home or at work, some options for data selection. You don't have to have your own DEM made. You don't have to use the JPL DEM if you're working in another site, for instance. You can download other models. There are global models. There are also local models. You have to do the research for that. An option that's available globally is GEPCO. But it won't be used for our tutorial. Tides are available usually through water level gauges. You can find them on the website of NOAA. You can also use the output of a tide model. Some are available at global scale as well. Here you have the example of FES 2014. River discharge are also available through gauges usually. I believe in the future, SWOT will be able to provide such data as well. In our case, we won't use waves because ANUGA is not able to take them as input, but other models could be able to. For instance, Delft 3D that will be presented tomorrow has an wave input. So you can get this data from buoys or also from global models such as WaveWorks 3 here. And the last one I'm presenting here is wind. Again, ANUGA is not able to do that. ANUGA is only water flow. But you can find data on various websites. I put here NOAA, but yeah, it's not the only one. The domain meshing is also a step that's important. The domain meshing corresponds to all the points where computation is going to be performed. So the more the more resolution you have, the better the model will be usually. But it also comes with the fact that it's going to be heavier to compute. So depending on whether you have a lot of computational power or not, and the complexity of your model, you will have to do some try and errors. With a measure that's pretty simple. It's like uniform mesh, but it's triangular. So triangular meshes are useful because you can refine them locally. Here I provide an example where it's in the Mississippi region, and the part of the deltas of Wax Lake and Atchafalaya are refined compared to the rest of the domain. So this was done with Ocean Mesh 2D, which you can download. It's a MATLAB software. There are other models, other software to do that. But again, it's not the point of this workshop specifically. In case you are interested, you can always Google those names. Something I discovered recently is that QGIS also has some abilities to edit such meshes. So you can actually use QGIS to edit a triangular or unstructured mesh if you need to. All right. Next step is the friction calibration. So once your model is running, you will see that it's not accurate everywhere. That's because you were not able to take into account all the complexity of your domain. Whether it is because you have different types of surfaces that impose different friction force to the water flow, or other reasons you were not able, for instance, to have enough resolution somewhere. Friction can help you correct part of those biases by allowing you to impose some some friction to in specific places. So in our case, what we did here is that we took a land cover map as well as a water mask map, and we combined those information in order to create a friction map where we have different classes. In that case, we have ocean, large rivers, small rivers, lakes, but also we have forests, broadleaf herbaceous, freshwater grass, and so on. And so all of those have unique friction that you can calibrate. So you can run the model once, see if it goes well. You can identify places where water should go faster or slower and tune those manually in the process, yes. And so the last step, when everything, all of that is done, the last step that remains is model validation. So for that, you need an independent data set to be compared with your model, whether it is discharge or water elevation, anything that will hopefully show you that you're doing things right or wrong. In that case, I'm showing the calibration that was the validation, sorry, that was performed for the model that I presented earlier. So the JPL models. You have here against the results of the model for water elevation with the CRMS network, which is a very dense, very nice network of water level gauges. So the model at the location of each gauges, the model is compared with the elevation that was observed, and we see if that goes in the same trend. We did the same with AirSWAT, which is a JPL sensor that was mounted on the plane and flown at the time of at the period of the model. And so you can compare in the same way whether this sensor measured the same water elevation as the model simulated. So in that case, when you have a straight line like this, it's ideal, basically. All right, so step 3, now it's time to do it ourselves. So I went through all this. I won't go back for a very long time, but first thing we need to do is download the workshop material. Hopefully now it's done for everybody. Once it's downloaded, you unzip it and place it wherever you want to be working on your computer. Then we need to install the Python environment. So all of this, again, is available for people who weren't here. It's available in the instruction document. So all you need to do is go to the ANUGA segment of this document and follow the instruction. Download the YML file here, create the Conda environment after having installed Anaconda, of course, and then test if the installation was done correctly. So I'm going to assume that this is done by now, but you can leave a message in the chat or raise your hand if that's an issue. We need a few data sets to be downloaded. There's the DEM. In that case, for the DEM, you go on this link. Again, that's available in the instruction file. And you download those 2 data sets that are framed in red here. So there is one that's called deltaic multi-source DEM Atchafalaya Terrebonne Basin 2021 v1.tif. And the second one that we need to download is deltaic multi-source DEM water mask v1.tif. So the DEM is the first one, the water mask is the second one. Once those are downloaded, you need to move them into the data subfolder of your the workshop material that you've unzipped. So you go in the workshop folder under tutorials. There's 3 subfolders that are numbered. You go into number 1. And in this number 1, hydro modeling, you will find a data subfolder. Yep.
If they are running in Google Colab, do they need to download?
No. So I'm going to go through this right after, but
okay, thank you.
No, quick answer, you don't need to download anything if you're running under Colab. Another data set that you need is the center lines. So you need to go on this website. The link is available in the instruction document. Under data here, you will slide down to the Mississippi Delta and hit download of the river centerline V1. This will download a tar.gz or GZ, document. So this is an archive. If you extract it or double click on it, if you're depending on your operating system, you will extract it. So it will open another or create another folder in which you have 3 more documents, including a zip file. So you need to extract that zip file, which will create another directory. And so this directory need to be moved into the data subfolder. And lastly, we need these 3 extra data sets. So including the vegetation classification map that we'll need for generating a friction map. So all you need to do is hitting this link that's available in the instruction file. We'll need the AirSWOT L3 water surface elevation dataset. It's an or an LDAC link, so it's the same website as the one we've downloaded the DEM on. And so you need all the files that are available on this page. There shouldn't be too many. And lastly, we need the CRMS water level gauges. It's another Google Drive link. So it's another archive. You need to unzip it, and whatever folder it creates when you unzip it, you move this into your data subfolder. Once this is done, we're almost good to go. Once this is done, so you need to open a prompt or a terminal window. The way how to do that is explained in the instruction file. So it depends whether you are working on Windows or on Mac OS. But it's fairly easy. So you open that window following those instructions, and you will type in conda activate ANUGA DX. So this will turn on your environment, the local environment that was created for this workshop. Then we will move at the location. So we will move into the folder of the tutorials. So you will type in CD space and then the path to the tutorials. So you need to be aware of where you put the workshop material directory. So in my case, for instance, let me do that. In my case, the tutorials here, so the path is shown at the bottom here. So if you're working on a Mac like me, you can just right-click on the last one and copy the path. I'm going to do it with you. So I have, what did I do wrong? Oh yeah. Rookie mistake. Okay, so here I've activated my environment. I know it because from base here, it went to ANUGA DX. Then I want to move from wherever I was into the tutorial directory. So here I have the path of it for my computer. It's gonna be different on your computer. So once I'm in, I should see tutorials here right after the name of my computer. And now we're going to launch the Jupyter Lab, which is an environment that allow you to run some Python within your browser. So you don't have to install anything else. And to do that, we're going to type in Jupyter Lab. So if some of you are familiar with Jupyter notebooks, it's basically the same. It works the same way. The difference is that you can go through the tree of your directories more easily in Jupyter Lab. So if I hit enter here, it opens my browser and goes into this page. So it's possible you won't have it opened. It will look like this.
Is everyone getting that?
It's also possible that you will be here instead. So you should have a page that looks like that. So you should be at the step where on the left panel here. And what we want to do is go in the first. Is everyone at this point? Is there any issue? Yeah. Oh, okay. So did you type in Jupyter Lab in your, and it's, oh, it didn't find it? Okay. So what you can do in case it didn't find it, it might be because it's not properly installed. So you can try, open another one here. You can try install it manually.
No, you should be in. Yeah. So make sure you have activated the ANUGA environment before doing this.
Yes. They do.
Sorry, you have an extra letter. Yeah.
It's hard without a screen.
You're going to have a very sore neck.
Okay, so yes, you need to first make sure that you activated your environment. You will know it because it's written on the left side here between parentheses, ANUGA DX. If you're not, if it's not activated, it's going to be written base instead. And so from here, you need to type in Jupyter Lab. So Jupyter space lab and hit enter. And if you still have an error, what you can do is type in this.
So that's pip
Yeah.
Oh, so
Pip. Pip install. I'm gonna forget everything.
and then Jupyter Lab with no space.
Right.
Yeah.
Pip install Jupyter Lab, and Jupyter Lab doesn't have a space in this case. If I do it here, it will tell me everything's already installed. Is there any more question? Okay, can you raise your hand if you're able to reach this step, please? Okay, so you were not? Okay, gotcha. All right, so I'm going to move forward. In case there is any more problem, I can always come and see you personally once we have a minute. Can you tell me when we have the break time? Oh, we did. You want to do it soon? There is a difference, but in our case, it's going to work exactly the same. Okay, so you want to take the break now? What time is it? Okay, in 5 minutes? Okay. Yeah, I mean, I have 2 more slides with Colab. And from that point, we can, okay. Okay, so assuming that you were able to reach this step, you're going to want to open the first tutorial notebook. So those files here are called notebooks. And here's what they do. So Jupyter works in a sequential, as like a sequential list of lines of code where you have cells. Each cell works independently, but so you will be able to run cells. And so when you run one cell, you run all the code, you read all the code that's written in that cell. So if you want to isolate some lines of code, you need to create extra cells, okay? It's very easy to do, you will see. These notebooks already contain code that I've written in order to perform a list of tasks, which will eventually, in the case of the first notebook, it will create a modified version of the DEM that will be enhanced in terms of hydrodynamic in hydrologic connectivity. Sorry. So yeah, as I was saying, the content of one cell is read all at once. When you hit play, the play button is on the top of the page. It also works in a way that everything that was applied before remains in memory. So if you have created a variable that stores a number, for instance, it will remain saved in the notebook, in the session of the notebook, until you kill the kernel, it's called. But so if you don't do that, it should keep it saved and reusable. So the sequence that we have 5 notebooks here, and they all are built on top of one another. So in order to run the second one, you will need the first one. The third one needs the second one to be run first, etc. So we will just go through all the steps step by step. So first, open the first notebook. And if you're not able to install all of this and open the notebook, an alternative way that you can do is use Google Colab. So Google Colab is an online platform that allows you to run such notebooks without having to install anything. All the notebooks that are presented today are available for Google Colab. So if you go on the GitHub page of our workshop, you will find links to Google Colab. Let me show you. Where's my here? So that is the page where you downloaded the workshop material, right? If you go under tutorials here, you will find all the tutorials we've made for this. You can go under hydrodynamic modeling with ANUGA, for instance. And in this page, you will find the Colab version of the notebooks. So you can open one here in another tab. And after a bit of loading, you'll see the notebook. It's exactly the same. The only difference is that it doesn't save anything locally on your computer. So anything that you will do here will be erased at the end of the session. You are able to download data here from the subfolder that will be created here if you want. But it's a little bit trickier and less flexible. So I would encourage everyone to use Colab if you can, to use the local notebooks if you can. But if you can't, that's also an option. And with this, I believe we can have a short break before we start doing the simulations.
How many minutes?
That's a good question.
15.
So we'll do a break for how much? 15? Okay.
All right,
We'll be
let's do
back-
a 10-minute break then.
10 minutes?
Well, because we're behind.
Okay, we will
We'll
be back at 8:20
No, 10:20, 10:20.
or 10:20.
For those on Central Time, we'll be back at 10:20. For those on Pacific Time, we'll be back at 8:20.
Oh, okay. Yeah, that's true. Okay, so now that we've installed everything, downloaded everything, and opened Jupyter Lab, I think originally you're going to arrive on this page. And so we want to go into the first directory here and open the first notebook here. So the first notebook will again edit the DEM and enhance it in order to improve hydrologic connectivity. There's a bunch of information on the notebook, on the data sets. At the top here, you don't have to read it through right now, but in case you didn't download all the files, you can still find them here. So I'm going to go through it with you for once. There's going to be some slight differences between the Colab and the notebook version, but don't worry about it. And so once we've done it once, you're able to go back and change a few parameters if you want, and rerun it yourself. So we can do the second notebook with your customized parameters. So this cell is only for Google Colab, actually. It will recognize whether we are working under Colab environment or not and install a bunch of things on Colab. Then this cell is importing and defining all the directory paths and importing all the necessary packages that we need for this notebooks. So you need to click on it. It's gonna show a blue bar on the left and hit the play button on the top of the page here. It's gonna be thinking for a while. You'll see a little star sign here. And once it's done thinking.
If you want this one, it's been adjusted.
Okay. Once it's stopped thinking, here you go. It will show a number, which is the number of times a cell has been run so far. So we've run this one, that was the first one. This one, that's the second one. And so you can keep track like that. If I want to run it again, I can. And it's done it. Now it's the third time a cell has been run. So you can know which one was run before another one this way. There's a few information in between. You can read it, but I'm mostly here to make the comment myself. So for this part, it's only available out of Colab. Colab doesn't have to run this cell. If I mean, you do, but you won't be able to draw a polygon. So what this cell is doing is showing you with a nice map here of the Louisiana coast. And our region of interest is here. That's where we have DEM information all along this part. And so what you need to do here is select the polygon option on the left, draw a domain. So your domain needs to include a little bit of the sea and a small part of the river as well. So I'm just defining here something really rough. And once you're done with your polygon, you need to click on the first node that you had created, the first point, and it will close it. So one of those boundaries is going to be the tidal boundary. And so you need to think about it ahead of time. That's the domain definition that we've talked earlier. So of course, everything is not isolated here. Like I was talking about using a domain that would be as isolated as possible so you can control all the parameters. But it should be good enough for us. So it isolates this part of the river and the delta as well. Plus, we have a gauge station I didn't mention, but the Eugene Island gauge station is located right here, somewhere around here. So what we're going to do is use this station and force this boundary to the same water level of as the station. So once you have your domain defined, you can define it on the other river delta here, or even somewhere else if you want. It doesn't really matter. It's just like, yeah, choose somewhere you like and hit save to shapefiles. If everything is done correctly, you will have a message indicating you that everything was saved in the correct folder, so the data folder. So once you have saved everything, the polygon, we're going to clip our model domain. So move to the next cell, make sure you have the red bar on the left, and you hit play again. So the number has changed here. It means everything ran correctly. We don't have any error message, so it's good. This cell, what was it doing? It was importing the DEM and some background image that will be useful for making nice figures. The next cell actually clips the DEM to the boundaries that we've defined. So we'll run it again. It's thinking for a little while, and then you have a message. So don't pay attention to this warning. Warnings are usually not a problem. We might have some other warnings down on the way. So now that everything has been clipped, we want to see how it looks like. So I'll run the next cell, and this cell is a specific data visualization cell. So it's going to generate a little map and save it in a directory that's called, I think it's called visuals. And so that's what it looks like. So that's the domain I defined, the DEM of the domain I defined. And you can see the background image here. And the color map shows the elevation. Okay, so now if we take a look closely, we see that some of those channels might be a little poorly defined, or we might want to carve them a little bit for whatever reason, as I was explaining earlier. So the next steps are doing just that. We want to import the center lines. The center lines are they are going over all the smaller rivers in the Mississippi Delta. So that's just taking some time to load the data set. It's also processing it a little bit so that the center lines are actually clipped within our domain boundary.
A quick question.
Yep.
For the data within the data folder, does every individual file, can it be in a subfolder or does it all need to be within?
The TIFF files are within the folder, and the CRMS have their own directory,
Okay.
and the center lines have their own directory as well.
Can you open your data folder right
Sure.
there, just so we can.
So there is some extra stuff here because we've created the domain boundary.
Okay, so for example, the DEM files need to be directly within the data folder. So I think a few people, does it work now? Okay.
Yeah.
Thank you.
Okay, so we've imported everything regarding center lines. Now we are going to so clip the center lines and calculate the width of the river channels using the water mask. So every node of our centerline file is going to have one value of channel width. And this way, we're going to be able to polygonize that vector and rasterize it eventually. So here you go. I've defined here a few, I've defined here a few parameters that you can change. For instance, there is the min width, the minimum width that you want to be able to carve your DEM with. So you can move this up if you want. Here it's set to 100 meters. The maximum width, 250. So again, you can put it higher up if you want. What it means is that anything that's narrower than 100 meters is going to be enlarged to at least 100 meters. And anything that's larger than 250 is going to be discarded. There is a max depth here. So that's going to be carving, that's the width, the depth at which we're going to be carving our DEM. And the bank slope proxy is in non-dimensional parameters that allow you to control the slope of the bank on the river sides. So 50 is fairly gentle slope. If you want, you can put it to say 5 or 10, and it's going to be a steeper slope. Did I run those? 9. Up. So we'll run this one. And this one. So that's the step at which we've measured all the width. Now we can buffer the center lines with the width we've measured to create polygons. Another visual. So you see that all the channels that were larger than the max width I set are left untouched, and all the narrower channels are enlarged. This cell is useful to rasterize everything. So from a vector type of data, we go to a raster type of data, and we'll use this raster to create an artificial topography of the channels. So this will be only setting values where we had our polygons covering. So you see, it doesn't go anywhere else than in the channels. So it also doesn't go farther than 250 meters in width. And it is basically a U-shaped profile that you can control the slope of. So here, again, it's pretty gentle slope. So for this workshop, it's not meant to be necessarily accurate. It's mostly for demonstrative purpose, but you can change this to something that's more relevant to you. And so once we have this, we are going to combine it with the original DEM. And so what we're going to do is essentially take, for any pixel in our domain, we're going to take the minimum value of depth between this artificial DEM and the original DEM. So that's the purpose of this cell. Again, there's a warning here. It's not a big problem.
Oh, quick poll. How many people are using Google Colab versus their own computer? So Google Colab and everyone else is on their own computers? Okay, because the Google Colab is a little slow, so they're a little bit further behind.
You can launch everything at once on Google Colab and just review cell by cell. Okay, so here we have a visual to compare, and hopefully you should see some differences, especially within the wetlands here. Some of the smaller channels have been carved significantly, and now we're sure that water is going to be able to flow in those if the meshing is done correctly. So all we need to do now is saving the results, and those two cells are here for that. So we save the results, delete the files that we don't need anymore. And with this, the first step is finished. So what I can do now is give you a few minutes if you want to change a few parameters. Say you want to move the upper limit of the channel carving width. You can rerun those cells and output something different. And once this is done, you can go and open the second notebook here. Double click on it, and it's going to be a similar story. Yeah. Yeah. So if anybody needs help, yeah, let me know.
For anyone who's having issues with the shapefile, all 5 or 6 of the .shp, .shx need to be together.
So there is a question in the chat. Are you able to see the question?
Such file or directory, I did not find a buffer active in the reverse and center line directory.
Okay. So, okay, the TIFF file wasn't found in the directory. So I believe that this could be an issue for this case where the person did not run maybe one of the previous cells. Oh, you did? Oh, really? Okay. So what's the solution? Okay, so there might be an issue with the spaces in the file names or the folder names maybe. So the advice is to move the deltaic workshop folder into another directory where there is no space in the name. Thank you, Mark. Okay. So the next step here is going to allow us to generate this friction map I've talked about a little bit earlier. So let's go through it again. First cell is again for detecting whether we are on a collab or not and installing a bunch of things. Then we import all of the necessary packages. There's a few information here, why we need to do it, how we do it, and the data sets we're going to be using. And then we'll load a bunch of data. So that includes the background imagery for visualization. We're also loading the water mask that you've downloaded a little bit earlier, extracting some information from it, its extent, resolution, etc. We're loading the center lines that were buffered, the TIFF file that you've just created. And then we're merging those with the water mask to make sure that we have something consistent. And the last step here is to calculate the distance to the shore that will be useful for our morphological classification. So we're going to basically detect smaller channels versus larger channels. We can even add more classes to that, depending on morphological characteristics. So I won't go into details if you're interested in how it's done, you can go deeper in the code. Those functions are available if you want to dig into it in a subfolder here that is called utils. And in utils, you have a bunch of Py files that contain some functions if you want to dig into it. But for our purpose, we're going to keep all of those parameters and run it. Yeah.
So at the end of the first one, when you're saving the results, where should that ASCII file be saved?
I believe in model input.
Yeah, so that's what it looks like, but for some reason, some people's are saving in the data folder. I don't know why. I think maybe just dragging it is fine. Yes, so some people's, it might have to do with them, I don't know, running out of order, but just if your file is not in this folder, the .ascii file, you just drag it into this folder. Some people's are saving into the data folder.
Thank you. In case those files aren't present in the model inputs, it means they probably are in the data folder. So you just need to select them and drag them to the model inputs. If you don't do that, the model won't run. And quickly show that all the figures that we've created are saved under visuals here. So yeah, so our classification is basically classifying the ocean, large channels, smaller channels, and everything remaining is offshore islands. So we have a morphological classification. But what about vegetation types now? So first, I'm going to run this so it combines all of those. And then we're going to go into the vegetation mapping. Okay, so we have a nice classification with 3 classes, the ocean, the large channels, and the smaller channels. Now we're going to add on top of that the vegetation. So let's import vegetation data. So this should be a TIFF file that you've downloaded from the Google Drive and put in the data folder as well. And so this bit of code will separate the different classes. So you have the forest, the broadleaf herbaceous, the grass, the freshwater grass, salt marsh grass, the tall grass, and the aquatic vegetation. So we're going to give a number to all of those and put them on top of the water classification. So we have a water and vegetation map that will be the base for our map, our friction map. And then we can save everything. So if everything goes correctly, you shouldn't have any error. You should have a nice map created like this and saved. Is it in the input folder? Yes. Friction map is saved here under the model input folder. And with this, we are done with the friction map generation. Yes, the vegetation map is based on AVRIS. It's a data set that was made by Daniel Jensen from JPL, and it is available on the the ORNL DAC. The links are in either the notebooks or the instruction file. So once this is done, so in this step, there was not too much flexibility to what you can do. You could potentially change the width of what you consider small versus large channels, for instance. I would recommend just to keep the one you have at this point. But if you want to try it, you can. So let's open the third step. And this will be the actual model run. Yep. No, it's only a classification. So you have numbering from 1 to 9, I believe, or 8. And those are just indicative of the class ID. We are going to be defining the friction values here in this part. As a function of vegetation type, yes. Is there any more question? Okay. So again, for the next step, Google Colab step, we're importing all the necessary packages, importing our model domain that we've defined earlier. And since we're going to be defining our model here before running, we need to do a few things. The first is to identify the boundaries. So this is what this step is for. So you have a map, a bit like previously, except it already has your model boundaries here. So what you want to do is take again the polygon and select the sides where you want to input your tide. So here I just have one segment where it's going to be forced, but you could have a very complex boundary here with as many segments as you want. It could also be curved. It could be linear like this. It really doesn't matter. All it will be doing is identifying those nodes in the mesh where we will force water elevation to whatever we want. So here we're going to be following the water elevation that was measured by the tidal gauge. So once you have defined your polygon, you save it as a shapefile, and it should save it under data, the data folder. Next, we'll import everything and make sure it worked. So this should be plotting a map showing the boundaries and their classes. So here I define the bay type of boundary and the side type of boundaries. So the bay is what I selected earlier. That's where we are going to force the tides, and the rest of it will be considered a wall. There are more than 2 types of boundaries for in modeling. ANUGA allows you to use different types of model boundaries. The only thing is that it gets a little bit unstable with other types than walls. So that's what we're going to be using today. But feel free to try with like transmissive boundaries, for instance. Oh, that's going to be later down the line. So another boundary condition that we need to define is the discharge. So here you again have your polygon the defining your domain. And we're going to put a segment this time. So we have to draw a polyline. We can do it on just one simple segment, but again, we could also be using multiple nodes, like a squiggly line if we wanted to. All I'm going to do is click once, a second time, and then a third time on the last point I've used. And then we save the polyline as a shapefile. That's saved under data again. This one? The polyline, yes. So let's run it again. If you made a mistake, you can always do it again. So you go back on the cell, you make sure that you have the blue line on the left, and you run the cell again, so it resets everything. And then you select polyline. You draw your polyline, so you click on one point, on another point, and to finish, you need to click a third time on the last point. And then you save the line.
Hey, Antoine, can we take a quick minute? There's some issues for PC users.
Oh, okay.
In the third notebook, second cell, I think. There's an issue with the path for the utilities folder. Oh, it also could be that they have. Yeah, so the folder is actually called utils, right?
Yes.
And not utilities. Also, if you have a PC, the slashes have to be the other way. It might just be easiest to find the folder in your computer and hard code it in. So just copy and paste.
So yeah, if anything of those don't work properly, you can always comment them out. So you hit Control or Command on a Mac and slash, and it's gonna put like a little I don't know the name of that sign in English, but it's gonna
Pound
a hashtag.
sign.
A pound sign. And so that means that it's commented out and it won't be read by the computer. So for instance, here, if I wanted to use another validation directory, I could just comment this one out, type the name of the variable, equal sign, and then between
And yes, if
quotes.
you're using a PC, you also need the double.
Yeah.
What is this for backslash? What I don't know, the two of them.
Like this.
The other way.
Oh, the other way.
Yeah, it just depends on your operating system.
Okay, yeah.
So if you know your operating.
It's hard to debug, yes. But essentially, what I meant here is that you can force the directory that you want by just writing the path of your directory. Is anyone else having issues?
Yeah, you should find where that file is stored on your computer and just copy the whole path and do equals that path. So it should be up in there. So you can just copy that whole path. And
Are you guys able to make it run?
I install it. I've originally utils instead of originally wrote utilities
Oh.
instead of utils.
Wait, I'm gonna go around. I'm sorry.
So I commented this out. This was the line that was,
And then
but it's different than the line you had, which is strange.
Okay.
Yes.
So now I'm just trying to code the path.
Okay. Did you download this like a while ago?
quotes to it.
I maybe downloaded it a couple,
Try that, and if that doesn't work,
couple
you might,
days ago,
you might need to
maybe.
double.
Not a real long time
So-
ago.
You see, you need
But you were able to
two
fix it, right?
slashes,
Yeah, but it might just be.
but I don't know that.
This shouldn't.
So it's
Well, just fix these two, right? That by install should just be a file path, right? In its stations.
Yeah.
Is working?
Let me see if someone else has the same issue. You were able to run until. So yeah, at least it's working, right? So yours is not working, is that right?
Just says like it can't find it.
So what you can do is, okay, let me show it on the big screen. It seems that a lot of people are having issues with the first cells. So it looks like it's coming from this lines. So what you can do is identify visually where this file is. I'll show you where it is. It should be under, oops, utils here, and then ANUGA tools, and you have the install file here. So if you're able to find it, I believe whether you are on Mac or a PC, you should be able to get the path from properties or informations. So in my case, that would be, I could just have copy the path from here, but from the properties on a PC, you can do the same. So you copy the path and you can just force it here. So
So it seems like that doesn't, even hard coding it doesn't work for the PC users.
Really?
1, 2, 3. Is it working for you? You have a PC. Okay, so it doesn't work. Any PC users successfully do this step? What step will that be needed? At what
just before running the model.
So no PC users have successfully done that step. Is
Okay.
that correct? Any PC users have success?
Oops. Okay. So I think we're going to be able to make it run anyway. We'll just not define any variable or varying friction instead. So, okay. Let's go back to where we were. So we have defined our discharge line, the transect where water will enter the domain. And then now it's time to define the mesh. So as I was saying earlier, mesh, the mesh tool that's built in ANUGA is pretty simple. There are some options to make it to make the mesh a little more complicated, but this is fairly unstable when it comes to complex regions like this. So we'll just keep it simple for our case. What you can do is define the ideal length of your triangle sides, that's an average value. And so this is where you can do it. I put it to 200, but you can experiment with smaller or larger triangles here. Just be aware that smaller triangles mean more cells, which means more computation time required. Yep. Yeah. That's a very good point. Doing 200 meters won't resolve the narrower channels than 200 meters. So we will run into issues, and that's where your try and error comes into play. It's like you can change this value to whatever you want. Right. Yep. That's a very good point. So let me run this. And so it tells us how many nodes and cells and triangles our mesh contains. So here it's a fairly small mesh. You can work with up to like the mesh that of the larger domain that I presented earlier is around 3 million points, and the same order of magnitude for triangles. So in order to solve to run the model on this, you might need a supercomputer. So the next step, maybe a little information about this. This is fairly simple. Again, if you wanted to use a more customizable methodology, let's say you want more resolution in the channels and maybe a coarser resolution on the islands here, you could use one of those tools. There are more that exist, but Ocean Mesh 2D is the one I showed earlier an animation of. It's a MATLAB package, so you need to use MATLAB to do it. There is a Python version, but it's under development. Otherwise, the University of Austin developed another mesh refinement tool that's specifically designed for ANUGA. But I let you go on this GitHub repo to see how it looks. You have other tools that exists. I won't go further than that, but yeah, it's fairly well. Like there's a lot of tools. Okay, so this file is important because that's where we define, this cell is important, sorry. That's where we define all the model parameters, the dates at which we want it to be ran, the tidal gauge that we want to be using, discharge gauges, all of that will be indicated in here. So the first line here converts this cell into an active Python file. So what it does is that it doesn't read information that is in the cell. It just creates a Python file that we will be able to load later on. So in that case, I defined everything to run for 1 day with a 60-minute step. So you could, if you wanted, you could put that down to say 5 minutes and see how it looks. I put 60 minutes so the output file is not too heavy in the end. But if you have some room on your computer, you could definitely go to a lower value without any problem. So I defined it for spring of 2021 at a specific date that we have validation data at, but you could define it on any other date if you wanted, as long as there is we have information from the tidal gauge at this date and the discharge. Okay, so let's run the cell. So again, it only writes a PY file. It doesn't actually save any variable. So we have to import that file and read it. That's what this cell does. So if you want to edit this file later on, you always need to run this cell and then this cell again. Okay. Now we are going to interpolate our DEM that we created and edited earlier to the mesh of our domain. And as was mentioned earlier, you will see that there are some problems because our mesh is 200 meters in resolution, while the smaller channels are only 100 meters. So some of those won't be resolved at all. And you see that you have a pretty coarse result. For the purpose of this workshop, it's not a big problem. You will be able to tell that at the end, the validation step will tell you how far you are from reality, basically. And the reason why it's so far from reality is because of that, because we don't have, first, we don't have a very isolated environment. We are making some really big assumptions here. We don't resolve the deep complexity of the landscape of the coastline here. But if you want, you can experiment with different values for resolution and see how it goes. So now we are going to download and set up all the discharge and tide inputs. So that's what those lines are for. It saves everything into a CSV file that is available in the model input folder. And from this point, we should have enough information to start working. Oh, maybe I should do the plots first. Yep. So this is what the signal looks like for the discharge and the water level that we want to use. So we have like, yeah, a couple tidal cycles. Here I give some information about the friction. So for some of you, we are going to be disabling that functionality in the model because we would need to. So the ANUGA model doesn't allow you to use the Baptiste equation, which is a modification from the Chesy equation, a friction definition that allow to take into account the variability in vegetation, basically. So for those who are not having issues with the first step of this notebook, you don't have to disable this step, but for the other ones, we will do that. In the framework of the deltaic mission, this the friction was actually calibrated through a try and error process. So in order to do that, it was first calibrated manually with no information regarding vegetation. And then it was adapted from vegetation. So the friction here is defined using a few arrays of data, which represent, you have here, friction coefficient, the stem density, stem height, stem diameter, and those are measurements from the field. So in situ measurements were taken for all of those parameters and inputted here. And then a calibration scaler was used to adjust when we wanted the friction to go down or up according to the calibration process. So I'm going to be running this cell. I mean, everyone can run this cell actually. It's later on, okay. And if you are working at a different date, let's say you're working in the fall season instead of the spring season, you can comment this out and use the fall season variables. The thing is that vegetation during fall season has different parameters than during spring season. So yeah, it's useful to just change those. Did I run it? 14.
The intersection. Oh, that's the. Yeah. Oh, look.
So
Yeah. So the polygon you're selecting,
disable it.
what point of your model boundary is titled. That's why it's a polygon. So that you can do basically an intersection. Model boundary and your sides, and then it selects those nodes. Title.
Okay. You want me to go through that again? Can you please raise your hand if you are having trouble with the install.py file? So 1, 2, 3. If you're not able to make it work, basically, can you raise your hand?
So who's still having
1,
issues
2,
with the?
3, 4. You do?
So did any PC user get it working?
Okay. So even with that error raised, you can okay. Well,
Did you get the?
it looks like it's only a few people that are affected, unfortunately.
Okay, so
in
I
the
don't think
back.
any PC user has gotten it correctly to find that file, but everyone can move past that
Okay.
so far.
Okay. So it looks like it's not a hard issue that you can still make the model run. Okay. Well, let's keep it the way it is then. Then we need to initialize the model. So we're going to tell it what's the initial condition of water level. So you could put any value here, really. You could put 100 if you wanted. That would mean it would fill up your model with 100 meters of initial water elevation, and then everything would hopefully go out of the model. But for this, we are going to be using the first measurement that was observed at the water level gauge. Okay, so I'm gonna run this cell and go to the next one. This is where we set the boundary conditions. So here we have the reflective boundary type of boundary condition. This is all the walls around our domain. You could use something else like a transmissive boundary type, but those are going to crash in our case. So I would advise not to for this. But in other types of models, let's say not ANUGA but Del3D, for instance, you could definitely do this. The inlet operator here is defining the discharge. So if in your model you have 2 channels instead of 1 where you want discharge to be inputted, you're gonna need 2 of those, right? You can just copy paste it, give it a different name, and so you will also need to to do this step twice. So you have like two discharge transects that are defined with two different names as well.
All right, can we ask, can we go back a little bit?
Oh, okay.
We have another issue, for, at least for Mac users, I don't know if it's PC, the tide cell.
Okay.
Can you scroll up to?
But
Or
so
sorry, yeah, so downloading discharge data and the tides. It is an issue with tides underscore NOAA. It's looking for the V
oh,
parameter. It says that it doesn't exist.
yeah,
Is that something they would have
yes, that's
if they didn't download something maybe?
okay. Let me check. Yep, I know exactly what it is. Just give me a sec.
Hmm? Okay, can you down to the one? Okay, yeah, so this is this one, yeah. So if you, once you've defined the tide, so you need to go up to the previous one and draw a polygon around the area you want to have tides. That polygon actually has to overlap with part of your model boundary, and that will select which nodes of your boundary are tidal.
So exactly.
No, no. So take the polygon one and just do a rough rectangle around the bottom half. It's fine.
Bigger than.
Yeah, so as long it has to overlap part of it. And yes, the model might weird because then the bottom ones aren't tidal, but that's fine. Then
Okay.
you save shape. Okay, now rerun this one. And yeah, so you, when it plots the mesh, you want to see that some are green and some are red. Unless you're colorblind, then you can't see that. And if none of them are red, then it hasn't defined any bay. Yes, so now see how those two that were within your polygon are red. So now you have a tidal boundary. And then you might have to.
If you're having issues with a column named V that is inexistent or not taken into account, those lines should help. Oh, it was here already. Those lines should help you. And if you're having a problem with them, just comment them actually, and that should run smoothly too.
How long should the model simulation take?
This one with the parameters we have, it depends on your computer actually, but on this one it runs in 15 minutes.
Okay. And but the progress bar should update?
Yes.
Okay. Did it change? Okay. Perfect. So
Yeah, so if it doesn't work, so they're here actually, the two lines. So if they I mean, if it doesn't work with them, you can comment them out. And if it doesn't work without them, I believe that's what you need to do. But for some reason, it doesn't work.
okay, but you unfortunately you have to have something in the if statement. So just go up to the if statement.
Okay, so I
So
think we
you
figured it
have
out.
something in the if statement.
Yeah. Yeah, I just realized that. Okay, so if that doesn't work, so you need to comment out all of this and unident this line, and that should do the trick. Want to say that?
Can you type it out, Mark, or put it in the chat?
Yeah.
So for PC users, the path has been discovered. And Mark is going to put it in the chat. If you're not logged in to the meeting, maybe can you copy and paste it onto the screen or something? Or just show the chat even on your.
Okay. So for PC, people who have a problem with this last bit of code in this cell, you can comment out the fpi install here and replace it with a hard-coded version that Mark is going to be writing in the chat. Do you need it? Okay. That's weird. Okay. So it is going to be looking like this. So you have one apostrophe, one quote. Yeah, okay. It disregards the spaces, okay. That's good to know. Okay, 2 people solved the issue with that already. All right, so okay, so can I move forward? Is there any more question? I haven't.
Okay.
So yeah, we'll define the initial boundary conditions here, define the discharge inlet, and define also the friction. So this little function here is going to basically distribute all the values of friction onto the map that we've created in the previous step. Those values are here, basically. So this calculates a friction from vegetation attributes for the vegetation classes. Otherwise, it takes, I believe this is Manning values for the channels, for instance, or the ocean. So you have Manning values for the water surfaces, and you have vegetation Chesi values for the vegetation classes. And so if you are looking for ways to set a good first approximation for Manning values for, like, say, large channels, you can find those into tables. If you Google it, you'll find it pretty easily. There exist a number of already defined good assumptions for those. And those have been also manually tuned. Okay, so now that we have done all the setting up, we can evolve the domain. So we are setting up the time that we want it to be running at, and this is an iterative process. It's going to be loading a loading bar, and you will be able to see at what point you are in the simulation. So I will run this, and you see, and so this should be actually taking a few, maybe 10 to 15 minutes. If you increase the resolution, it's going to be taking longer. If you decrease it, it's going to be shorter. If you increase the simulation time, it's going to be longer again, etc. So this is like a trade-off that you need to define. So if you have taken a larger domain than I did here, it's also possible that there will be more nodes and cells in your mesh, so there will be more computation to perform. It's going to take longer, basically. Yes, it is possible to run ANUGA on a supercomputer. I'm not going into how to do this in these files, but it is definitely possible. Yes.
How quickly it's running on your machine.
Oh, yes. Yes. Okay. That's a good question. It could be because you have like a larger domain. It could also be because you are running with smaller resolution or higher resolution, I mean. Did you change any of those?
I didn't change
It's possible. How much longer is it for you? Okay. Yes, yeah. The longer it goes, the longer it takes. So it could be that because it takes more time to add up to an already. What it is doing here is that it's saving the output file at every step. So you could actually stop it now, and you still have the output file saved somewhere. Actually I'm going to do that, so we don't have to wait for the whole time. But yeah, so I interrupted it willingly, but if you go in the in the main folder here, you will find an SWW file, which is the output of our model. And so it takes a little bit more time to add information to a large file already than to a smaller file. So that's why the processing time is increasing a little bit. So for the next step of our model, we need this file to be saved in another place. So that's what this cell is doing. If I run it and go back here, you see that the SWW file disappeared, and it actually just went into the input, the outputs here. Oh, yes, that's a good question. You can type, give me a sec. Where's my mouse? You can just click on this stop button. Yes. Yes, it will have saved whatever was already simulated. So you can interrupt it whenever you want. It actually restarted from where it was with a little bit of coding, but in that case, we won't go through that extra step. If you have it run all the way to the end, it's better, obviously. So was everyone able to get to the creation of an SWW file? Can you raise your hand if you don't have an SWW file created? You don't? Okay. Oh, okay. Oh, but you should have one already. Yes, because you are at step 2. It's gonna be in the parent folder or in the main folder of the tutorial. Okay, here you go. Yeah. Good. Yes. Yes, I believe so. Was everyone able to run it here? Yeah, okay. Yeah, you see, that's one of the issues that you need to run into in order to understand how, like, to change the parameters. Did you have like a large domain? How large was it? Yeah, okay, I see. Yeah, of course. But if you're running it still, it's going to be interesting to see. Plus, yeah. So when once it gets red, the loading line, the weight bar, I mean, it means it's stopped. And you know it also because there is no star on the top left. So what's the error here? Oh, it looks like your model has 0 depth. Some places it has loss of conservation issues.
Okay.
So it means that there is like an issue when defining the parameters of the model domain. Maybe you took a little bit.
Into the
Maybe it's also that you don't have depth data in some cells. You know, like you.
seems
I don't look. Yeah.
reasonable.
Yeah, it does seem it sometimes it's possible that your DEM stops here
Yeah.
and you click like right under the
Yeah.
and so it inputs some NaN values into it, and so it just messes up with it.
So I'd have to like redo the polygon.
Possibly, yes.
Okay.
Maybe put it a little bit
Close to the.
yes. That's all I can see, like on the top of my head like that.
Okay. Yeah.
I'm sorry about that.
That's okay.
Were you able to have it running? So you're already at the next step. That's good. Okay, yeah. So it works. Happy about it. Is it working also here?
I'm okay.
Okay. Yeah. So yeah. But yeah, you're not able to change everything, unfortunately. You could actually, if you wanted to, you need to download, like when you do step 1, you need to download the files that you edited, say the DM, for instance. And once you're at step 2 or 3, you need to upload them and replace the files that already exist. You could do that if you wanted. But yeah. Okay. So once everything was run in the model running notebook, we're going to analyze the results. So the next notebook is about this. We want to basically just create nice animations of the water flow. So this is what it is all about. First, we're checking if we're on Colab or not, then importing the necessary packages. Then we are importing our model results. You see that mine only has 4 time steps. This is because I stopped it early, but yours, if you didn't do that, should have as many time steps as it needs. So if you're running it for 1 day at like an hourly resolution, you should have 24 time steps. It doesn't really matter for the visualization purpose here. So what we're going to do is import all of that, recalculate the tidal gauge using the PI file that we saved earlier, the settings of the model, and then we can calculate in a little animation. So again, mine only has 4 of those, which is unfortunate, but oh well. And so, yeah, it does show you a little animation. You could, if you wanted here, it's just for visualization purpose, but you could replace the BG IMG file path with the file path of any GeoTIFF image that you have, and it will basically overlay this animation with a map. So let's do the same. So this is water level. So the colors show how the stage of the water level variability through time and space. But you can do also the water velocity instead. And so this first step is just like importing the center lines, because since we want to see velocity, we want to see vectors, little arrows. And so the arrows are only going to be plotted in relevant points for efficiency purpose. And so here we go. We have an animation of the water velocity with little pointing arrows that show us where the flow is going towards to. Okay, and that's it for this notebook, actually. It's a fairly short one. Again, you can experiment, put longer, create a longer model, put more time resolution. You'll see like smoother animations. Obviously, those are very coarse in time. Okay. Yeah. Okay. Okay. Let's stop here, and we'll go back to the validation and last step after lunch.